Hi, welcome. In my series on science, we will today talk about a man named Eratosthenes in ancient Greece who gave us a pretty good estimate of the size of the earth. But before we do that, let's talk about what the ancients knew about the shape of the earth. So, when they looked at the earth, they believed, and the earth appeared to be flat. I mean, when you looked around, it looked so flat. When I look at a tree at a distance, it appears parallel to me, and therefore it doesn't appear tilted or anything, and so I have a reason to believe that it's flat. And people also thought, when they looked at the oceans, that the world probably ended in a huge waterfall, because when they looked at the ocean, the earth obviously didn't extend to infinity, because obviously we saw the sunset every day. The sun went down the horizon, and so earth definitely was limited in size. Uh, so this also bothered people, because now they were very afraid to sail on the oceans, because they thought that, oh, maybe the oceans end in a huge waterfall, and if you kept sailing far away, then you will eventually get down that waterfall and drop off the earth. And that's why they were very worried to take on the oceans. But obviously this hypothesis, or believing that earth is flat and it ends in a waterfall, has its flaws. Like, if earth really ends in a waterfall, why don't the oceans dry up? That's a very important question, uh, and I don't have an answer for that. And similarly, uh, some other people, some wise people at that time, they argued that the earth is round. It is not a flat disk like a plate on which I eat food. It is more like a ball, or like a soccer ball, and it is spherical and round. Why did they believe that? We'll talk about that. But the question is, how do we argue about something like this? Suppose you and I are fighting over this. Suppose you believe that the earth is flat and I believe that the earth is round. How do I convince you that the earth is round? Obviously, one option that I have is that I say, okay, I'm going to travel around the world, and if I reach the same point where I'm standing right now, then obviously the earth is round, because I came back to the same place where I started from. Is that a feasible option? I don't think so, because what happens if you drown in the ocean? What happens if the earth is so big that by the time you reach to this place, before that you die of old age? Or what about the fact that, just in case I am wrong, what if the earth is flat and I drop off the earth? Well, I die. So this is not an option. How do we argue about this? This is where science comes in. We can settle this, and we can settle it in the scientific way. In science, essentially, such situations occur often, where you cannot really observe something directly. You wish you could, but you cannot. Now, but you will still like to understand the natural phenomena around you. So what you do is you list all the hypotheses, measure all you can, list down all the facts you can see or hear or observe, and then based on all these facts and observations, you try to come up with a theory that can explain these facts. If you cannot observe something directly, you try to basically observe related facts, or things that are related to it. So essentially, science can be thought of as doing detective work. When a detective is called to a crime scene, he does not have access to a videotape telling him that, look, this is what happened, here is the tape. No, it doesn't work like that. The detective, has to work based on the clues that he sees. So suppose he goes there and he sees, oh, I see there's a dead body, and there is a knife there. So I think my hypothesis is that this person has been stabbed. Now, given the facts, that is a good hypothesis or a good theory, because it explains the facts that you see. If you come up with a theory that, I think this person has been shot, that is not an acceptable theory, because it does not match up with the observable facts. Science works just like that, that you observe some facts, and those facts are correct unless your apparatus is wrong, which we won't consider the possibility of. Your facts are correct and not changing, and the only thing that can change is theory. So you come up with theories that will explain those observations and experiments, that will match up with your experimental facts. In fact, not only that, if you have a scientific theory, it should match with all the observations or experiments that someone does in the future. Uh, in science, what happens is that as we progress, we have a certain theory. As we do more experiments, we generally learn more. We generally do a new experiment, and then we suddenly see, oh, this new experiment does not fit with the theory. Then you go ahead, either reject the theory completely or you modify the theory so that it can explain the new observations. That's how science works. It's a learning process. It's where you learn about the way of the universe, and it's a continually learning process. So anyways, coming back to our hypothesis, we have two main hypotheses that we are considering today. One is that whether the earth is a flat disk like a plate on which I eat food, or whether it is round like a soccer ball. So let's list down all the observations that I see around me. Observation number one: the earth appears to be flat. Well, that is an observation, yes, and this observation clearly favors hypothesis one, that the earth is flat. Having said that, I should also mention that second hypothesis is still not ruled out. It is still possible as follows. If the earth is really big and its curvature, the rate at which it curves, is very low. So think of an ant on a huge giant ball. That ant will think that the earth is flat. And so even though obviously this hypothesis supports even though this observation supports first hypothesis, both hypotheses are still possible. Second hypothesis, second observation, sorry. The oceans do not dry up. I mean, they were present at the time of my grandfather and father, and they are present at my time. So oceans do not dry up. So this observation does not support any of the hypotheses, but it definitely puts a big question mark on the earth being flat theory true, because if the earth is truly flat, where does the water of the ocean go? Third hypothesis, and the Greeks at that time noticed one thing, is that if they saw a ship arriving from a far distance, they were able to see the sail of the ship much before they could see the hull. Now, this is hard to explain if the earth is flat, because if the earth is flat and you see a ship right at a distance, you should be able to see the ship, both the sail and the hull, the bottom of the ship, at the same time. It shouldn't be that you see one portion and not the other. Think of a tree. If I see a tree, I either see both the top and the bottom. It's not that I just see the top and not the bottom. But for a ship at a large distance, it was observed that the top appears first and then the bottom. And Greeks argued that this can only be if the surface of the earth is not flat, but it's slightly curved. Next observation: North Star appears lower in the horizon. So Greeks noticed a very curious thing, that when they traveled south, as they traveled south, there was a star in the sky which we call the North Star, which as they traveled south appeared lower on the horizon, and as they traveled north, it appeared higher in the sky. In fact, we know from observation today that North Star is directly overhead at the North Pole, and it is at the horizon, at the eye level, on equator. Now this fact is very hard to explain on a flat earth, because the surface of the earth is flat and the rays from the stars are coming from a huge distance. They are coming parallel. By traveling little bit, 100 or 200 kilometers on the surface of earth should not have any impact on the apparent position of the star. If you are on a flat earth and you are here and the star appears here, if you move a little bit, the star will appear straight overhead, unless the earth is curved, in which case when you are at the North Pole it appears overhead, and as you go, you go to the middle of the earth, the equator, you see it at the horizon. And this is a very strong observation and a very strong argument in the favor of second hypothesis being true. This will be very hard to explain on a flat earth. Observation number 5, and this is due to Aristotle. Aristotle was a Greek philosopher in about 300 BC, and this was the time of Alexander the Great. He was the student of Plato, and Plato was a student of Socrates. These are all great philosophers, and Aristotle was the teacher of Alexander himself. So in 300 BC, he wrote a book called titled On the Heavens, and he gave two strong arguments why he believed that Earth was round. One we have already talked about in observation 4 about the North Star. The second comes from lunar eclipse. He saw all the he when he looked at the lunar eclipse, he came up with the theory that lunar eclipse happens because of the shadow of the Earth. That much he knew for sure. Now, by looking at the lunar eclipses, he realized that the shadow of the Earth was always round. It was, if you, for example, look in this photo, the Earth comes in, and the shadow is always round, and even while going back, it's round. And this happened in every lunar eclipse. Now, this is what he argued: if the Earth was a flat disk, then the shadow of the Earth will be sometimes elongated, sometimes very tiny, sometimes long, but not always spherical. If it is always spherical, that means that the Earth, whose shadow we are seeing on the moon, is spherical. And this was a very strong argument in the favor of Earth being round. Now, if you were the detective, I ask you, you have seen all the evidence, what side will you choose? Clearly, the evidence is very strong in the favor of 2. Now, the only true way to find out what shape of the Earth is you take a flight, go really high into the sky, and look at the Earth in its full glory and find out what its actual shape is. But Aristotle did not have that luxury. Now we do, and we have taken such a flight. What was the truth? What is the truth that we find? Well, the Earth is a round sphere. So anyone at that time chose the fact that Earth is round was right. Anyone who chose to believe that Earth is flat was absolutely wrong. This photo was taken by the crew of Apollo 17, and it's a very famous photograph, also known as the Blue Marble. So next we talk about what is the size of the Earth. How do we give an estimate of size of the Earth? So this is due to Eratosthenes. He was born in 276 BC, about 50 years after Aristotle's death. Aristotle died in 230 BC, and he was also the director of a very great library in Alexandria. Alexandria was a city built by Alexander, and we know that it had a very great library, and Eratosthenes happened to be the director of that library. So he noticed a very curious thing one day. What he noticed, he actually read this in a book, that on June 21st, in a city in Syene, which was in south of Alexandria, the sticks did not cast any shadow. I mean, vertical sticks had no shadow, and this was rather peculiar. What was observed is that as the hours grew towards noon, the shadows went short and short and short and short, and by the time of noon, the shadows were totally gone. The sun was totally overhead. If you looked into the well, you could see a reflection of the sun in the well, and therefore sun was vertical, totally vertical. Now this posed a question for him, that will sticks do the same if I do this experiment in Alexandria? So he put up a stick in Alexandria, and he found out that sticks in Alexandria at the same time, on the same day, do pose a shadow. They do cast a shadow. Now this Eratosthenes could not explain, because according to him, how could it be that stick in one place cast a shadow and stick in another place do not cast a shadow? Because see, let's take it with an example. Suppose the rays of the sun is very far. We know that the rays, when they come, they hit the Earth parallelly, because sun is very far. Let's just assume that if Earth is flat, Alexandria and Syene, let's say, are those two cities. Syene is in the south. Then if Syene does not have a shadow, Alexandria should not have a shadow. Similarly, if these rays of the sun come parallel to the Earth, in that case, if there is a shadow in Syene, there is a shadow in Alexandria, if the Earth is flat. How is it possible that on one place on the surface of Earth there is a shadow at the same time on the same day, while in other place there is no shadow? And to this, Eratosthenes could only think of one argument, which is that the earth is not flat, the surface of the earth is curved, such that in Syene, which is to the south of Alexandria, when sun's ray hit, they hit parallelly and directly vertically, and there is no shadow. And in Alexandria, when the rays come, they hit at an angle and it makes a shadow. Not only that, he also realized that if I could find out the difference of lengths in the shadow, if I know, for example, that there is no shadow here and the shadow corresponds to if to 7 degrees or few degrees, then you can compute the or you can give an estimate of the size of the earth. Because think about it, if the earth is more curved, then the difference in the shadow length will be much larger. If the earth is not curved at all or very little curved, then the shadows will be of similar length and the difference will be smaller. So greater the difference in shadow length, greater is the curvature of the earth. So what he did is that he hired a person to find the distance between Alexandria and Syene, and that person walked and paced out the distance between the two cities, and it was found to be 800 kilometers. And he found the angle from the shadow lengths, the difference of shadow length, he found the angle to be 7 degrees, roughly 7 degrees. So if you knew that roughly 7 degrees is 800 kilometers, and you know that 7 degree is roughly 1/50th of the entire sphere. An entire sphere is 360 degrees. 7 degrees is 1 in 50 roughly of it. If 1/50th of the full sphere is 800 kilometers, of the full circle is 800 kilometers, how much will be that full circle? Well, 800 times 50, and that's 40,000 kilometers. And when I look at it, I am just amazed. I mean, bravo, bravo, bravo. 40,000 kilometer is a remarkably close estimate that Eratosthenes gave us. Think about the tools that he used. He used sticks and shadows and sun and some thought experiment. And it is so close. The true estimate that we know is 40,075 kilometers. So he did something truly amazing for his time. To conclude, Eratosthenes achieved something rather remarkable for his time, and Alexandria at that time was one of the greatest seaports on the earth. People traveled from Greece and Egypt and Alexandria towards the east side, towards India, etc. And no one had really traveled towards the west side. But if you knew that the earth was a sphere, it was not a flat disk, would you not be tempted to take great voyages and maybe even try to attempt to sail the planet? Because it's just 40,000 kilometers. One could do it. And Christopher Columbus did take such a voyage. I mean, he was a reader of old books and maps. He had read all the books from ancient geographers, including Ptolemy, Strabo, and Eratosthenes himself. And he was very fascinated by the idea of reaching India and China by sailing westwards and not eastwards. He wanted to sail west and west and west, and he knew that if the earth is round indeed, which people tell us and he believed to be, he will eventually hit India. And that is, he was just fascinated by it. And that is when, during his conquest, he wanted to come to India, but Americas came in the middle and he discovered America. In fact, had Americas not been in the way, Columbus would have drowned in the ocean because his estimates of the earth were much smaller than what earth actually is. So, question: would Christopher Columbus try to sail the earth if he didn't even know that the earth was round? If he still believed that the earth is a flat disk, would he dare to make such a voyage? Probably not. So, thank you. That was lecture today. We'll see you in the next lecture. Thank you.